Thank you for joining our webinar on modernizing existing hydropower sites with high-performance FishSafe turbines. My name is Kate Sturr, and I'm the Vice President of External Affairs at Natel Energy. I'm joined today by my colleagues Abe Schneider, who's co-founder and Chief Technology Officer at Natel, and Sterling Watson, who's our Principal Engineer, as well as Pat Donahue, our Vice President of Business Development. And we're really looking forward to sharing our work to improve downstream fish passage throughout the hydropower industry. So please feel free to use the chat function to ask questions throughout the presentation, and we'll also invite you to come off mute and ask additional questions at the end of the presentation. So Natel is a technology and engineering company based in California. Our mission is to support healthy rivers, promote biodiversity, and decarbonize the grid, with the goal of addressing the dual crises of climate change and biodiversity loss. We do this by focusing on hydraulic design of turbines that improve the survival of fish and other aquatic organisms that are moving downstream. We apply a scientific approach to creating unique turbine runner blade shapes that optimize both performance and fish survival. And we also provide engineering services to plant owners to help them assess their options for installing these high-performance fish-safe turbines, including looking at the economics that might inform the decision-making. We also conduct fish passage and performance tests on scale model turbines at our hydraulic test loop in Alameda. And these tests help inform our design process and validate our turbine designs. Then we partner with existing turbine manufacturers to make the turbines that result from our design process. So as I mentioned, our work is really rooted in our desire to use sustainable hydropower to address climate change. Hydropower is a key part of the global energy mix. It makes up about 50% of all renewable energy globally and 15% of the global electricity supply. So if we are going to reach net zero by 2050, hydropower has to roughly double in capacity, according to the International Energy Agency. And while we need hydropower to continue to provide that flexible baseload power, we also need to acknowledge the impact that hydropower has on ecosystems. So this bar chart shows the growth of hydropower over the last 120 years, alongside the decline of migratory freshwater fish species since 1970, when we started collecting that data. The decline in migratory freshwater fish is certainly not entirely due to hydropower, but there are some ways that hydropower has really contributed to that decline by fragmenting rivers, adding to habitat loss, and in some cases, directly harming fish that pass through hydropower turbines. And this last piece of harm to fish that are passing through hydropower turbines is what we are working to solve by making hydropower turbines safe for fish at Natel. So it might seem self-explanatory, but it's worth calling out that the primary locations that are suitable for developing hydropower sites are on rivers where fish migrate. And this map shows existing hydropower facilities in the US, Canada, and Europe, plotted against the range of several notable migratory fish species, including eel, salmonids, eulocines, as well as different species of sturgeon. So this overlap means that we need solutions that preserve biodiversity while producing hydropower.
Here we see the most common approaches to downstream fish passage. Trap and transport not only has a substantial capital expense, it also has low effectiveness of transporting the whole migrating population of fish and eels. It also introduces additional stress on the species that are handled. Plant shutdowns reduce revenue and also brings the risk of losing capacity payments for sites utilizing that type of revenue structure. These spillway flows can also have an impact on upstream passage by introducing false attraction and preventing fish from finding the ladder or lift system. Screen and bypass systems bring an increased complexity with a rise in OpEx costs, along with the CapEx costs necessary to design and build the system. Labor hours will also increase in order to keep the screens clear. In this scenario, the bypass flow isn't able to be captured for power production. This slide shows some real-life examples of what can happen with the current approach to downstream passage. The first photo illustrates that fine screens can easily clog with debris such as ice flows in winter or leaves from deciduous trees during the fall and occasional storms. The center photo is the intake to a bypass that is blocked with debris that floated downriver. Workers will now be tasked with clearing the obstruction, which introduces potential safety hazards to these employees. The third photo is what can happen when improperly designed fine screens are installed, leading to mortality from eels becoming impinged on the screens.
Zooming back out, let's take a look at the hydropower fleet. In this case, on the left-hand side, we have a scatter plot, which illustrates all of the hydropower plants in the United States above a megawatt in capacity, plotted by the year that these plants were commissioned. And one thing that immediately jumps out is that the majority of our fleet is aging and quite old already. The average age of the hydropower fleet in the US is over 60 years, and this is also the case in Europe. Hydro is a very reliable and long-lived resource, but one of the consequences of this statistic is that a large fraction of the fleet is undergoing or being considered for necessary upgrades, modernization in order to keep the plants running reliably. At the same time, we're facing an oncoming tidal wave of relicensing. In the United States, non-federal hydropower plants operate under licenses issued by the Federal Energy Regulatory Commission. And one of the consequences of relicensing is that the conditions of operation are reevaluated. And in many cases, the necessary conditions for treatment of environmental performance or environmental sustainability are increased. We've seen a trend towards the increased protection of downstream passage of fish, for example, at these sites. Taken together, the aging fleet and the necessary investment in modernization of the hydropower fleet, combined with the oncoming need to relicense the fleet, represents a very unique generational opportunity to make the right decisions with regards to what equipment is placed in service. And from the operator's perspective, a lot of times you only have $1 to get $3 worth of work done. You need to satisfy needs to modernize and rehabilitate your asset, to implement improved downstream fish passage, as well as upstream fish passage. And what we want to dive further in today is the possibility of improved turbine designs to allow for $2 worth of that work to get done with one investment.
So anyone who's familiar with work at a hydropower project knows that hydropower sites are all unique, and considerations around how to improve the environmental impact of these sites are always going to require looking at the various factors that are unique to the site and how they affect the fish. But one thing that every hydropower project has in common is that it has at least one turbine. And that turbine really sets the baseline for the downstream survival achievable for fish at that site. And so turbine design is something that really should not be neglected when looking at the impact of the project on fish. We included a quote from the EU taxonomy that frames this really nicely, which highlights that any measures that are going to be applied, such as technology selection for infrastructure in a hydropower context, need to consider the ecological impact of that design and how it's going to affect the ecological status and potential of the project on the waterway. So how do fish get injured by hydropower projects when moving downstream? The first thing you might think of is fish colliding with turbine blades. And that is a very significant issue that occurs with all types of turbines. This is when fish collide with the typically fast-moving, sharp blades of Francis turbines, propeller turbines, Kaplan turbines, and may suffer spinal fracture, lacerations, other very severe injuries. Another injury type that is important to highlight that we specifically see with elongated fish like eels is mechanical grinding, which can result in severing of the body. And this occurs when the fish or the eel collides with the leading edge of the blade and moves into a converging pinch point where it can be sheared between a moving and stationary surface. And then a third injury mechanism that's really important not to ignore is the injury that occurs from rapid decompression, which is called barotrauma. And this occurs in fish that have swim bladders. Most fish have swim bladders, and this is an organ that contains gas that will expand when the fish is exposed to the low pressure that occurs within turbines. And all reaction type turbines function based on this pressure change. And so this is something that may be more or less significant depending on the physiology of the fish, the depth to which it is acclimated, and then some of the design and operating conditions of the hydropower project. So as we look at the hydropower fleet in general and the issue of downstream passage, we thought it'd be really useful to look at where are the fish actually going when they're passing through these turbines, what kind of situations are they being exposed to? And so this graphic represents all of the flow that is passing through turbines in the US hydropower fleet. And we broke it down by the pressure head across the turbine and the flow rate through the turbine units. What you can see is that the vast majority, 81% of hydropower turbines in the US fleet are operating under low to medium head, so below 40 meters or about 130 feet of head, and are consuming flow rates in excess of 50 cubic meters per second or about 2,000 cubic feet per second. And so if you kind of take the first order approximation that the fish are distributed according to the flow, this means that most fish that are passing through turbines with that head and flow characteristic. So this is important because traditionally, as turbines have been unsafe for fish to pass through, the only way to protect them is to keep them out of turbines. And you do that with a fine screen. But fine screens become increasingly difficult to implement correctly as the flow through the turbine increases. And so this is not a comprehensive set of data that I've shown here, but these are examples that we were able to find that have proven success in excluding fish out of turbine intakes. What you can see is that for all of them, the flow rate is below 50 cubic meters per second or 2,000 cubic feet per second. And the characteristics of these screens are, in order for them to be effective for at least larger fish, is that they have a bar spacing no greater than 20 millimeters, and that they also have a very steep incline, 30 degrees or less. And this means it's a large and often very difficult to implement kind of piece of infrastructure. This photo that you're looking at here is from the installation of one of the turbine units at Bonneville Dam, which is one of the larger dams in the US. It's a really interesting photo because you can tell from the context that it's old, from the fact that these workers are not using any PPE and certainly not adhering to the safety standards that they would need to today. But if you look at the actual shape of the turbine and specifically the shape of the leading edge of the blades, it's pretty representative of what we still have operating out there today. In the last 100 years, we've learned a lot about how to improve human safety. We've actually also learned a lot about how to design for improved fish passage safety as well.
So there have been some notable efforts to improve the design of hydraulic turbines for improved fish passage survival. And on this slide, we're highlighting a couple of those. Both of these advancements came out of investments from the United States DOE in the mid-90s to the mid-2000s. First, the minimum gap runner, which is illustrated in the upper right of this slide, was an idea to eliminate gaps that are otherwise normally found on Kaplan turbines at the leading edge, where the leading edge intersects the hub and the tip. And by eliminating these gaps and pinch points, we're able to eliminate a direct source of risk to entrained fish. And at the same time, it helps to improve the efficiency of these runners. And as a consequence, this type of turbine has already been installed at some important sites in the United States as well as in Europe. Another idea that came out of the Advanced Hydropower Turbine Systems program at the US Department of Energy was the Alden turbine, which is illustrated in the bottom right of this slide. The Alden turbine primarily was an effort to reduce barotrauma by extending the length of the runner. So the pressure drop occurs across a longer distance. The location of the lowest pressure occurs at a lower elevation relative to tailwater. The runner also had a reduced number of blades, so the strike probability was reduced compared to a normal Francis turbine. But one of the downsides of this design was that it had really low power density. So what this means is that it would produce considerably less power for the size of the runner. And as a consequence, it's never been commercially installed. So Natel's approach looks to synthesize some of the learnings from both these successes and drawbacks of past efforts to improve fish passage survival through turbines. And our approach is pretty simple. It basically combines the idea of relatively thick blades with forward slanted blades, which allow for safer strikes at the high speeds necessary to be commercially relevant. So we're really focused on designing hydraulic turbines that have the same power density as conventional hydropower turbines. In other words, they could replace existing hydropower turbines in existing hydropower facilities, produce the same power, but do so with much improved fish survival. The way that this works is that out at the tip, where velocities are highest, our blades lean forward significantly in the direction of rotation, and this lean directly reduces the forces felt by fish, because the fish striking a blade at that location will do so in sort of a glancing manner instead of a blunt blow. At the hub, where velocities are inherently lower, the runner can have a more conventional slant angle, such as 90 degrees. And this design approach can be implemented across the full range of runner types found in the industry today, including fixed pitch propellers, adjustable pitch Kaplan type machines, which is what's illustrated here, as well as mixed flow or Francis machines. So to give you a more direct sense of how a runner designed with these principles compares to a runner following conventional or textbook design approaches, here we see on the left a side and axial view of a runner designed for fish safety compared to a conventional runner. Importantly, both of these runners are installed in exactly the same turbine. They produce the same shaft power under the same head with the same flow rate. These actual runners are part of a study funded by the US Department of Energy, in which Natel is working with the University of California, Davis to study direct and sublethal impacts of sturgeon passage through both of these turbines. And the table on the left summarizes both the range of tip speeds that were explored during the course of testing, so from 15 to just under 30 meters per second, and the survival of two species, American eel and white sturgeon, in which the Natel-designed runner was able to provide nearly perfect survival of these fish species, and the conventional unit showed survival on average around 70%. One of the characteristic aspects of Natel's experimental work is the fact that we often try to directly observe passage of fish through our turbines. And this is done with high-speed video. And here we can see one of those sturgeon involved in this test passing through the runner. You can see that the fish is clearly hit by the blade. It passes on through and is able to survive this experience. In contrast, here we see an example of the much misunderstood hot dog fish standing in for sturgeon. We do have the same type of footage of sturgeon. And basically what happens is the object is sliced. And most of the mortalities that we observed from the conventional unit basically involved complete severing of the fish in this study. So where do we go from here? What are the kind of designs and outcomes that are allowed by this approach to turbine design? Well, one of those is the ability for large hydropower projects to dramatically improve downstream fish passage success with almost no impact to operations and to energy output. On this slide, we're presenting an example of a runner that Natel designed for a very large utility on the United States East Coast, which has legal requirements to maximize downstream passage success for silver eel. This comes after more than a decade of successful restoration of upstream passage of young elvers past this facility. Natel was able to design a runner shape which preserves or maybe slightly increases the shaft power output of this turbine with no change to the water passageway while preserving use of the existing generator, and the runner can be bolted to the existing shaft line. This is also a really great example of how Natel works within the industry. Natel is a specialist in the design of turbines for high performance and fish safety, but we're partnering as a subcontractor to a large existing turbine manufacturer who is the prime contractor to the utility and will actually deliver the runner and commission the plant. So that particular plant illustrated the need to collect fish passage survival data at elevated speeds between 28 and 30 meters per second. And Natel added to its existing successful eel passage data with additional tests demonstrating nearly 100% survival of eels at such conditions. And this compares very favorably to single passage survival rates through a variety of turbine types tested both in North America and in Europe. As you can see on this scatter plot, which illustrates the blade peripheral speed on the x-axis with that important range from around 20 to 35 meters per second highlighted on the x-axis. And you can see that Natel's test results already show exceptionally good survival of eel under these commercially relevant conditions. So how do we actually go through the process of intentionally designing a runner for fish survival?
So what you're looking at here, kind of a behind the scenes look at our computational approach to simulating fish passage through our turbine designs and directly quantifying expected survival rates for kind of fish populations in question. So we'll get to it in a couple of slides, but we have a model scale test facility that has allowed us to conduct physical tests with actual fish passing through the turbine and quantify their survival outcomes. And so what we did here was we simulated the same parameters from the test, including the same geometry, the same operating point, and the same size distribution of fish passing through the turbine. What's happening here is spherical fish particles are released into the flow field and carried by the flow through the turbine. Velocity and pressure and other information are derived from the paths that they take through the turbine and then correlated to an expectation of survival based on exposure to those stressors. In the top example, this is a runner with 3 blades spinning at 667 RPM. The bottom example is a different runner. It has 2 blades and it's spinning about 50% faster. And what you can see is that the predicted survival rate from the computational model is very closely aligned with the actual survival rate that we observed. And this plot kind of expands upon what I just showed you. Those 2 tests on the previous slide were performed with channel catfish, but we've tested with a much wider variety of species, including salmonids like rainbow trout and Chinook salmon, white sturgeon, American eel, and others. And what we've plotted here is the mortality rate observed from physical testing, that's the teal bars, and then various model predictions of that mortality rate. And so the orange bar represents our computational model technique, and you can see that it agrees very well with the experimentally observed result. And then the yellow and gray bars represent 2 much simpler spreadsheet-based strike probability and mortality prediction tools. And you can see that those models are much less accurate. And so this really kind of underscores why we have worked to create a more sophisticated computational based tool to predict mortality, as that's kind of the crux of what we're doing as we need to design these turbines. And so I'll walk through a few examples of testing that we've performed with different species. There's more information that you can find at the links and on our website. But the first one to note is a study that we performed of American eel passage at small scale on our test stand. This study we performed in 2021 in collaboration with the Pacific Northwest National Lab. And we really wanted to observe and understand how eel pass through turbines or pass through our turbine designs. And what we did was we tested a pretty extreme example where the size of the eels was on average about the same as the diameter of the turbine. So the eel length was about the same as the diameter. And consequently, the eels used in the study all contacted at least 1 blade. We quantified the survival and injury rate, as well as qualitative observations of how they pass through the turbine. And we saw 100% survival for all the eels used in this study. Another study that we performed, this one was a little different. This one was performed in the field with another very important and sensitive migratory fish species in life stage, which is the juvenile alewife, kind of representative Holocene species. And in this study, we saw 100% 48-hour survival rate of the fish that passed through this turbine with really nice high-speed video. And then finally, we've performed extensive testing most recently last year on juvenile white sturgeon. This work was performed as part of a study in collaboration with the University of California, Davis. And at the variety of speeds that we tested, we saw over 99% survival of these sturgeon. That work is in progress for journal publication later this year. This is an overhead view of our model scale test facility that we have at our headquarters here in California. This consists of a tank, a pump, and the turbine. It allows us to operate the turbine across a range of conditions up to about 10 meters of head and a little over 1 cubic meter per second of flow. The way that we use it to test fish is we can insert one or multiple fish into the treatment injector, which is located upstream of the turbine. It's basically a pressure canister that we can place fish into, increase to the pressure of the pipeline, and then open a valve that releases the fish into the flow. They're carried from there through the turbine, where we can capture high-speed video of their passage and then extracted downstream of the turbine from the flow by a fine screen. And that allows us to get immediate observations of their condition. And so just for reference, a typical amount of time that it takes between when we see the fish enter the pipeline and then pass through the turbine and then exit the pipeline is usually around 8 to 10 seconds. So this allows us to immediately observe the fish's condition, something that's quite hard to do in the field. And then we also have a recirculating aquaculture system that allows us to hold the fish for extended periods of time, at least 48 hours, often much longer than that. So we can observe their condition over time after they've passed through.
The FishSafe runner design has been implemented in multiple field operating hydropower projects to date. 2 of these exist in the United States, one in Oregon at Monroe Hydro, and one in Maine at the Freedom Falls hydropower facility. There's also a unit operating in Austria as well. However, all of these units are fairly small. The turbine in Oregon is 6 feet in diameter, but the future is headed in a much bigger direction. On this slide, we're sharing 3 examples of more than a dozen different projects that Natel's involved in which we're designing FishSafe runner replacements for existing hydropower plants with runners over 3 meters in diameter. On the left is a horizontal full Kaplan machine, which I'll explain in more detail in the coming slides. In the middle is an example of a vertical double regulated Kaplan machine, which is for a project in Europe where the runners would replace existing Kaplan runners of a very modern design and are able to match the energy output of those machines within a fraction of a percent while passing fish with exceptionally high rates of safety. On the right is one of the first examples of this unique design approach being applied to mixed flow or Francis style units as well. So how does a runner replacement project actually get done? Over the next couple of slides, I'll explain how this works for a real site. This is a project in the United States, which has a couple of horizontal Kaplan units, which are currently operating with very wide trash rack spacings that are not expected to exclude any fish from entry. The official prescription for downstream passage mitigation is to install 3/4 inch spaced fine exclusion screens and a bypass. But there's no available example of a screen system of this size that's been installed. If it could be installed, there would be a reduction in annual energy output of at least 3% as a consequence of combined head loss and lost flow to the turbines. So Natel was approached to help create an alternative solution that would help meet fish passage goals with less overall cost and complexity. So the way we do this is we work with the owner to obtain drawings of the plant, oftentimes 50 years or older drawings, which we then use to create a digital water passageway model. So this is a CAD model of the shape of the water passageway, which then allows us to create a candidate runner design, which is then optimized in an iterative process using state-of-the-art computational fluid dynamics tools. In addition to maturing the hydraulic design, we are also studying the resulting runner from the standpoint of mechanical competence. So structural, stress and strain, and manufacturability are taken into consideration as well. But very importantly, of course, we're using these digital tools to compute a quantitative estimate of fish passage survival, which is then included in the feedback loop for runner shape optimization.
So the species of particular concern at this site for downstream passage were American eel, juvenile alocines, so shad and river herrings, and adult alocines. And the site had been evaluated for the turbine passage survival of its existing units, and it was found that the survival rates were below 75%. However, the target survival rate for all of these fish is over 95%. And so what we did is we simulated populations of each of these species and life stages passage through the turbine, which is what you see in the animation here. And we evaluated their risk of mortality from both blade strike and barotrauma sources. And through iterative design, we were able to come very close to that 95% survival target. This really kind of exemplifies the real considerations that you make when looking at designing a runner that can fit within an existing turbine context and improve the survival rate for all the migratory species of concern.
So of course, it's really important that the solution produce energy efficiently, that it operate reliably and without cavitation. Here we're showing some of the cases that we would typically study in a feasibility study stage. So in addition to edge cases, maximum flow, minimum tailwater, which might represent the worst case cavitation conditions, but of course also peak power and the best efficiency point of the turbine. And what we can see from the result of all of these studies and the optimization of the runner geometry is that we're able to create a FishSafe runner, which is also a high performance conventional performing runner. This particular project resulted in a runner that had almost 93% hydraulic peak efficiency, really wide range of stable operation. And ultimately, the predicted annual energy output of the project is several percentage points greater than if the project was required to implement the normally prescribed fine exclusion screens and bypass. So one of the really interesting things that this type of a breakthrough in runner design allows is for entire watersheds to be studied and to be contemplated for improved downstream passage continuity. Here we're showing an example of the Merrimack River in the Northeast US, which has, like many other watersheds, numerous hydropower facilities up and down, and important populations of migratory fish, which actually need to navigate, in some cases, the majority of all of these different projects. We're highlighting one of the projects in yellow here, where we're publicly working to provide turbine redesign solutions for the owner. I think one of the most important takeaways is that, as aging turbines in the fleet are considered for refurbishment or for modernization, it's really important that in the process of thinking through how to modernize these plants, that we consider fish passage in the design criteria, because it's a great opportunity to meet two different restoration goals with one investment.
So we talked at the start of the hour about the staggering decline in biodiversity that we've seen in the past 50 years. And about the need to increase hydropower production. So our vision is that when we combine FishSafe turbines with other mitigation measures like habitat restoration, more natural flow regimes, invasive species control, and dam removal when appropriate, it will be possible to really actively reverse the current trend of declining biodiversity while still generating flexible, renewable power to address climate change. So to adopt FishSafe turbines at a scale that can have a widespread impact, it's going to take significant collaboration that really builds upon the strong collaborative efforts that have been underway already for decades to improve turbine designs for high fish survival. And perhaps you can see yourself represented within one of these groups that are highlighted by these alewives that were part of our turbine passage study in Maine. And hopefully, as these fish are doing, we can all begin to swim in the same direction towards a future where fish-safe hydropower is the norm. So Thank you very much for attending today, and please feel free to come off mute and ask questions. Appreciate you being here.
Most of our efforts have been focused in axial flow type design. So this is propeller and Kaplan style machines. And the range of head for Natel style designs will be roughly similar to the range for conventionally designed propellers and Kaplans. We've begun working in the design of mixed flow machines, which have, of course, a higher head rating. And Sterling can comment on this a little bit more in depth. It is not necessarily the case that, for example, barotrauma is exclusively an issue for higher head projects and a non-issue for lower head projects. In fact, it's oftentimes a site-specific issue with both the fish of interest. Different fish species have different sensitivities to rapid pressure changes. Different sites may have deeper intakes or higher intakes. So the pressure acclimation of the fish that are entrained could be different. So it's not a simple answer in terms of what is the maximum head. I think that certainly at the heads where Pelton turbines would normally be applied, it's not necessarily where we're focused.
What I would add to that is, as you probably saw from the images we showed, the blades that we design have this characteristic very thick leading edge and forward slant. And that's something that we are able to implement in both Kaplan and Francis contexts. And that's really kind of how we elevate the strike survival aspect. With barotrauma, that's something that always needs to be considered on a site-by-site basis. And in our experience is not something that's driven by head, but is really driven by the minimum exposure pressure that the fish experiences in the turbine.
One last comment is that we're already in very detailed design for projects at 30 meters of head and preliminary scale design for projects that are over 40 meters in head. So as you could see, our company has made really significant investments in the testing of fish passage alongside hydraulic performance. And I think this is one of those areas where Natel is really distinguished, not only in the duration of time in which we've been carrying out this activity, but also the openness in which we're carrying out that work. We've been working with key participants from regulatory bodies right from the beginning. And one of the specific points of feedback that we got was to really focus on peer-reviewed publication of our testing work. And that is something that is unique to Natel. Natel is also, however, a small company. We do not have a large factory, and what we realized is that rather than attempting to start up a new turbine making company, the thing that we are creating that's new and of additional value to all of the other positive attributes that already exist in hydro, reliability, high performance, and so on, high efficiency, is this understanding of how to design for fish survival. And we can design turbines that are far larger than we could ever actually manufacture. And even if we could manufacture them, who would buy from us? Because we don't have decades of demonstrated projects under our belt. So the right thing to do is for us to work in partnership with existing original equipment manufacturers who do have all of that experience, but who have not necessarily made the similar level of in-depth investment into the fish survival aspect of turbine design. So this project here is a great example, just a specific tangible example of a turbine which is vastly larger than Natel could ever conceive of manufacturing or installing and commissioning and guaranteeing. And yet it is absolutely well within the capability of several handfuls of existing turbine manufacturers. And so this is one where it's an ideal partnership. Natel provides the scientific understanding and credentials on the fish safety side, and the turbine manufacturer provides all of their experience and competence in carrying out the manufacture and the commissioning and standing behind that physical equipment for years to come. And another key thing is that depending upon where you are, of course, hydropower is a global resource with very local issues. So owners of hydropower facilities may have many good reasons to work with one or another turbine maker. Hydropower turbines can be 3 megawatts, 30 megawatts, or 300 megawatts. And the same company that is best to produce at one end of that spectrum is probably not the best at producing at the opposite end of the spectrum. and yet the design approach for fish survival is pretty much the same. And so that's another good reason why it makes sense for us to have this role that we've created for ourselves. So I think this slide is a reasonable one to talk to. So the example in the center is one where the new runners, the new Natel runners, will actually replace runners that were on the order of a decade old. So quite recent hydraulic design.
Yeah, okay.
Yeah, and in this case, at the feasibility study design stage. So as I think you probably know, in the process of creating a new hydraulic design for a project, you're going to go from a pre-feasibility stage to a feasibility design stage to a for execution stage. And the amount of effort is greatly larger once you reach the execution stage than at the feasibility stage. At the feasibility stage for Natel, we are creating a full three-dimensional computational fluid simulation of the actual geometry, and in many cases, hundreds of geometry iterations and evolutions to get to that point. So it's important to understand like what we mean when we say feasibility study, and yet that's still not quite, as mature as it could be when it's released for manufacture. So at that level of maturity, this design will produce within a fraction of a percent. So say less than 0.5% difference in energy output compared to the conventional runner design. So there is a slight reduction in energy output, but it's starting to be within the error of measurement. And then importantly, it's the ongoing operation of the existing turbines. It's not guaranteed that those turbines can continue to operate with no screening and no bypasses. It is most likely that those existing turbines will have to have some kind of fish protection placed in front of them, which will cause additional energy loss far in excess of the 0.5% max loss from the new FishSafe runners. So that's a practical example. And I guess what I would say is that by the point that this project reaches execution, I think it's very likely that we could improve the design so that there's effectively no difference from the output of the FishSafe runners versus the conventional runner. Probably the first larger unit to be installed in Europe outside of that very small unit that already is running in Austria will be a project where a Natel runner will upgrade a very, very old plant. And so we should see a significant increase in efficiency there, but it's not quite the same scenario that you're asking about.
Yeah, that's a really good question. Barotrauma is very, in large part, driven by where the turbine is vertically positioned relative to tailwater. And so it's something that we can improve through careful design by paying attention to what proportion of fish are being exposed to those minimum pressures. But it is a hard problem. And often in our design process, it's really like one of the drivers of the design. In some cases, we're able to address that issue creatively. For example, there was a project that we were working on that was a Francis design originally, and we were able to design a new Francis unit that really eliminated the strike issue, but still had some barotrauma problems. And so the design that we created was actually a modified axial flow design that set the runner closer to tailwater. So it's always going to be a case-by-case issue when you have these projects that were originally designed close to that cavitation barotrauma limit.
You can just navigate to www.natelenergy.com/publications, and you'll be able to find our papers there.
Those studies go into detail on survival rate as well as things like injury rate. If you have any additional questions, definitely reach out to us directly. I think we'll also be providing the slide deck.
So there's not really a theoretical limit in terms of maximum flow capacity. We already have done detailed design for units with over 130 cubic meters per second per unit. And we know of situations where runners with 400 cubic meter per second discharge could significantly benefit from the design approaches that we've developed. Specifically in Europe, some of the main stem hydropower projects on large rivers, which have passage problems for endangered species, including some species of sturgeon, for example, we think would be great candidates for redesign, as well as main stem projects that have passage issues for European eel, for example, where we are absolutely confident that we could help.
Our understanding is at these projects with very high turbine discharge, there may be no other good solution to protect fish that are moving downstream, aside from improving the turbines.
Generally speaking, I think the right way to answer this is that the process of arriving at a price tag is ultimately going to be one which is going to involve an existing turbine manufacturer. The process of getting to a design which could allow for such a cost estimate, going from pulling in old drawings to ultimately optimizing a design feasibility stage runner, takes Natel 2 to 4 months of calendar time from start to finish. And then you can kind of imagine, roughly speaking, what that might cost. It's a very, very reasonable cost and a very small amount of time to include into the decision-making process. For non-closed loop pump storage, of course, if you're pulling water from a river, then absolutely you're going to have a fish entrainment issue.
Yes.
I'll just say it's not something that we've actively worked on yet. From the standpoint of direct injury to fish, I'm sure that there are ways that we can help. From a more global perspective in terms of the round trip survival efficiency, I think it's a potentially pretty tough problem to solve, but we'd be interested in looking at it if that was an area where we might be able to help. In general, fish passage at hydropower projects can be a quite complex issue, and we certainly aren't ones to claim that we can solve all of these problems. For example, we haven't really talked about upstream passage. However, downstream passage through turbines can be a really important part of a complete tool set to significantly improve passage problems overall.
Thanks so much, everyone, for being with us today. I hope you enjoy the rest of your Tuesday, and please do reach out with any further questions. We'd love to keep the dialogue going. Thanks again.